Let's now learn about what a sampling distribution of a mean value is. To begin, let's start out with a question like this. What was the national mean gas price on June 1st, 2020? So obviously, right at the moment that I'm doing this lecture right here, then we are already way past that day right here. But so think about the scenario where this question was brought to me that, of course, gas price today is already changing. But so what was the national mean gas price on that day, just a few days back? So in the attempt to find the answer to this question, this is what I did first. Back on that day when that question was brought to me, what I did was I searched through the internet, and there are a lot of resources out there over the web that we can collect gas prices. But so if you can look over to my computer screen right here, what I have on screen here is that on that day I collected and see back to the question here. But it's asking national mean, so it really means that wherever I'm at, I was not only going to look for gas prices locally, but I'm supposed to look for gas prices as nationally as possible. It's not possible for me to display all the states where I got these gas prices from, but what I have here is a collection of, I have 36 prices, 36 different gas prices from all over the 50 states of the United States here that we have. And of course, let's only limit our study here, our lecture here, our study here to only within the state of the United States right here. And so national mean gas price here, I was looking for that mean value that come out from all gas stations, from all gas prices, within the United States. And so I went through the entire nation. I used a couple websites, and I searched through the entire nation, and I collected about 36 individual prices. So any of these numbers, keep in mind, is an individual price. But after I made my collection, after I had my collection, then I calculated a mean value. I calculated a mean value being 1.69. And optionally, I have my quick calculator that's strong enough to give me a standard deviation value. So 0.25. So I thought I found the answer to this question. Mean gas price on that day, June 1st, 2020, was $1.69, according to what I had on my screen that I showed just earlier. But then I was thinking over. I gotta be watching out for this phrase right here. Simple phrase, but quite dangerous. It was asking, the question here is asking, what was the national mean gas price? Now, obviously, in the picture I had, my mean value here did not come out from all gas stations. The word national here, this term national here, really means, if I was doing it correctly, I was supposed to find the gas prices from all over the country. So think about, literally speaking, in these days, every corner on the street here has a gas station, and I must search through every single little town throughout the entire United States at every corner of the streets, and then collect all of those prices. That's where I can average out a mean and get the national mean gas price. So the greatest concern now is whether this can truly be the answer to the stated question. The number of individual gas prices that I collect to get this mean value was only 36 prices. Or in other words, this mean was only calculated from 36 individual prices. Of course, nationally selected, quite randomly selected. But so what I realize now is only having 36 different prices and obtain an average like this is nowhere near to the correct work that I was supposed to do, because it does work right here. it's intended for me to search through the entire nation on every corner of the streets to find the actual national mean. So I actually now realize that this question is intended to look for what we have learned in previous term throughout the quarter. This is a population mean that we're looking for. Because we have a lot of gas stations and gas prices everywhere is different. It could be different a lot, it could be different a little bit, but all throughout all gas prices in the nation, it's big enough data that we can consider as a population mean. And the legal symbol for that is the mu symbol. So that's the intended answer for this question. However, this mean I found here, as I said earlier, only came out from 36 prices individually. And so this mean only deserves its place to be regarded as a sample mean. So sample mean can represent a population mean, but it will never be the actual population mean. Or in other words, I have to put a comment here that so this population mean that we're looking for at this moment, even though I thought 1.69 was the answer, but now I realize the population mean here is still a mystery to us. For now, to me, it's still a mystery because I don't know. I didn't search enough. And also recall that sample mean, and as a matter of fact, you have also seen that slightly a bit when you were looking at the computer screen, but sample mean use a different symbol compared with population mean. Population mean, we're using the mu symbol, indicating the kind of mean value where we were able to average out all values. So here is thinking of that scenario, national mean gas price. We need to average out all gas prices throughout the nation. But here, this sample mean here is only from 36 sample prices. And so sample mean here, recall that it's the lowercase x bar here. And then the capital letter N that we use in our sample is now used as to describe, well, N equals 36. But in the concept of a sample, this is regarded as the sample size. And so now, as I pointed out, the answer to this question remains a mystery because the answer to that question is intended to be a population mean. I didn't find it. Now, the question is, if I use 1,000, if I search and spend my time to collect 1,000 gas prices on that day, June 1st, 2020, will that be enough to get me a population mean? Not enough. Still not enough. And what about 100,000 prices? Will that be enough? Still not enough in theory. And so the point is, we think of the population as a very large data to the point that we don't even need to know, we don't even know how big the population is. It's just something too big. And so even when you get to the tens of thousands or the hundreds of thousands, it's still not going to be enough. And so in the end, as long as we have a definite count of how many prizes we use, any of these, once you have a mean, it's only going to give a sample mean. No matter how large, here it's only indicating that we have a sample a lot bigger than the sample from 36 prizes, but in the end, it's only going to give us a sample mean. And the same with this 100,000 gas prices, but that collection right here, once again, will never be enough to give us a population mean value. And the average coming out of that again remains as a sample mean. And so the rule of thumb here is that anytime we're looking at a collection of data, we're trying to reflect, we're trying to represent the actual population mean value, but we only limit our work to our data to within some finite count of data observations or of data values, then our mean values will permanently remain as a sample mean. So mean value coming out from 1,000 gas prices remain as a sample mean. You might have a larger sample, you spend a lot more time and efforts to find this many gas prices throughout the entire United States, but once again, you only, and sadly, only going to end up with a sample mean. So 1,000 is where sample size n equals 1,000. Or even if you have 100,000, sample size n equals 100,000. And so in what I said about no matter how large your sample, your data that you collected from the population of gas prices is going to be, but as long as you have a finite count and your mean value coming out from that permanently remains as a sample mean, then it becomes hopeless to reach the population mean, because no matter how large you increase your sample, you still, as long as your sample remains a finite count, then your mean value there is a sample mean. Then why do we keep wasting our time looking for a larger and larger sample? So why don't we look back at our sample here and let's see what else we can do with only a small sample like that, but let's find out what else we can do. So now realizing that it's hopeless to find a satisfying population mean answer, it still right now remains as a mystery, and it's hopeless to find a collection of gas prices that's big enough to represent the population mean. So now let's turn our focus back to the current sample that we've had. So sample size here, there were 36 prices in that sample, and it gave me a mean value, and now I have to clearly identify that as a sample mean, because dangerously the question here is looking for population mean, but we only found a sample mean being $1.69 from 36 randomly selected prices throughout the nation. And the standard deviation from this sample here for now in our study here is for now optional, but it's good to write it down. So it's a sample standard deviation being 0.25. The average spreading, the average variations from values to that center of the sample. So now I actually realized, but hey, instead of keep looking for bigger samples, why don't we look at things this way? Another question is brought up as following. If we can find our sample being 36 prices, and it didn't take too much time to find a sample being 36 prices, and then calculator can quickly get us a sample mean like this. So think of this question. If there can be one sample of 36 prices for now, can we repeat finding a different sample? 36 prices again. So I'm talking about, what about another sample? Is it possible to find another sample? Oh yes. Let's all now look at my computer screen here. Let me show how I can use a computer software to quickly search for a different sample of prices. But now, when I mean what about another sample, let's set out for ourselves here a rule. Let's stay with 36 prices again. So I'm going to make my computer to search for another 36 prices, and that's what I'm trying to say. So here, quickly observe my data collection here. And now I come up with a different sample. So notice, now this is a completely different sample, but I can leave some time for everybody to count, but they are again, from the beginning to the end here, there are 36 prices. This time the mean value changed to a different value. And then the standard deviation is also different as well. So the only thing we keep here is that we stay with the same sample size. But in this next sample here that we just now found, sample size being 36. And we already had a different sample mean, and it's quite well expected that way. It's a completely, think about that as a completely different data, Or think about you send two different researchers to go out on the field and come back with two separate samples for you. So this is one sample from one researcher, this is another sample from a different researcher. And so this sample right here has, this new sample has mean $1.72. And that's why now, once again, to verify my point I was saying earlier, none of these values can qualify being the population mean that we are looking for, simply because a sample mean value changes its value depending on the sample, whereas a population mean value does not. So in this second sample that we have here, sample standard deviation being 0.31. So now with the first sample, having a sample mean being $1.69 and sample standard deviation actually along where I'm going, then I shouldn't need to write the sample standard deviation, because all it matters for us right now is looking at the mean value. And so, but importantly, I use 36 prices in that first sample. And so now formally, let's give that this is our sample, or that there was the description of sample 1, because that was our first sample that we brought up. Then we made another attempt on another 36 prices, and we found the mean value there in that second sample is to be $1.72. And so with the same sample size right here, so now I'm going to regard to this in the sequence of work right here, then this is sample 2. And let's quickly look back at my screen again, where I'm going to quickly find a third sample. So now observing my sample here, it's already changed to a different sample. I'm staying with 36 prices again. I don't need to be too worried about the sample standard deviation within the sample. But my sample mean here, once again, switched to a different value, changed to. So now for my sample number 3 right here, I found sample mean here is $1.68, where again I remained the same sample size, being 36 prices, and I have to now call this sample 3. So this is now what we're realizing. In this way, we're starting to question ourselves. How many more of these samples like this are there out there? How many more samples like these? And of course, when I'm saying like these, I already meant all the same, assuming that they're all the same 36 prices in each sample. But how many more samples like these are there, or still out there? And all I can say here is a lot, countless. So in that way, again, we don't need to hopelessly search for all samples out there. We just know that there will be many more waiting out there. But here is actually with 3 samples we have here, it's enough to start looking a little further into our understanding here. But so you can see that anytime we use a different sample, our sample mean change value slightly a little bit. Sometimes we might be lucky that we run into a different sample but have the same sample mean with any one of these we already found. That's completely okay too. It happens. What I'm trying to point out now is that if somehow you can search for all samples existing out there and each one of them give you a sample mean, then here, what I'm circling here is really, eventually we're going to end up with a population of sample means. I'm talking about what if we're not going to stop at 3 samples, but we're going to keep searching for more samples, and any one of our samples coming back gives us a sample mean. Then eventually or consequently, we're going to run into a what's so-called a population of sample means. And this population of sample means, in further informal term, it's a distribution. It's a distribution of sample means. That's a formal term in statistics, because the reason we use the term distribution now is that, and after you've learned the concept of continuous random variable, is now because we have these values happen at different probabilities out there. And so, of course, we're not able to find the chance that our sample means equals precisely one value, but we will be able to find out the probability where our sample means will fall above a certain range, or our sample mean will fall below a certain value. Like that. And so, what I'm trying to point out now is that we can have for ourselves a population of sample means by continuously searching for more samples and more samples. And or we can think of that as formally, we think of that as the distribution of sample means. And furthermore, I have to clarify that the entire purpose of collecting samples to find sample means is that we are trying to find what could be a satisfying answer to our beginning questions, the population mean of national mean gas price. And so any of these sample means reflect or represents the population mean, and the population mean, particularly in our study here, is for gas price. And so this distribution of sample means right here, informal statistic term, is what it is. It's a sampling. So what we have here is a sampling distribution. Okay, it's a sampling of distribution, and for our problem here in particular, we're studying gas prices right now. So sampling distribution of mean gas price. But now, most importantly, now we understand what a sampling distribution is. A sampling distribution is a distribution of sample means, or another way of thinking, it's a population of sample means. Those sample means represents the true population mean that we're looking for. And that's what a sampling distribution of a mean value is all about. Okay, so at this point, let's summarize a couple of key points here throughout our previous discussion. But we have seen that a sample mean value, any sample mean, represents the corresponding mu. And that's ultimately what a sample mean is for. A sample mean is used to represent some mean value, some population mean value. So that's one key point. And so the idea now we also need to nail, the next idea we need to nail down is that anytime we can pick up one sample or a sample, then there is another one. So bottom line speaking, there is not only one X bar value. There are infinitely many values or many X bar values. And so how I see that here is anytime we can pick up a sample, then there must be another sample existing out there, and each sample gives us a sample mean x bar value. So that's why consequently, or at the bottom, we can say there is not only one x bar value, there are infinitely many x bar values. And of course, I'm talking about these sample means values provided that they all come out from the same sample size. So provided all samples have equal sample size. And that sample size is capital N letter. And so that's the next key point that we need to highlight right there. And so now I would like to focus a little more on that second key point right here. The second key point is anytime we have a sample mean value, then keep in the back of your mind that there must be another value. And as a matter of fact, there is not only one x bar value, there are infinitely many. Infinitely many to the point that we can have an entire population of x bar values. A population of x bar values. And so now at this point, we are ready to give a formal general definition of what a sampling distribution of a mean value is. And so upon realizing that there is not only one x bar value, there are indeed infinitely many x bar values. And as a matter of fact, there is an entire population of x bar values, and provided that all samples have equal sample size, equal given sample size n, then here we're now ready for a formal definition of what it means by being a sampling distribution. So a sampling distribution of the mean and that's a one special terminology, so allow me to write it in red once again. And so a sampling distribution of the mean is the distribution of all sample mean values x bar of the same sample size, capital N. And of course, capital N sample size here is either decided or given. Okay, and so now once again back to the gas price, the national mean gas price discussion. So this mean right here was intended to be the mu, the national mean gas price. We couldn't really find, and we did not find any true value for the mu value right here, for the mean, for the population mean gas price. And so as a matter of fact, at this point it still remains a mystery. But what we found instead, we already found a sampling distribution. So I found my sample mean x bar 1 right here. And now I'm starting, in case I haven't done this before, now I'm starting to give a subscript index, now indicating that this is just simply my first sample that I found throughout the discussion. So my sample mean 1 was $1.69. So be aware that this is not only one single gas price. This came out as the average of 36 prices. And so we found a second sample, and the sample mean in the second sample was $1.72, and our sample size there again remains 36. And so the rule of thumb here is anytime that we are constructing a sampling distribution of mean values, then we need to agree upon only one sample size. And so I also went as far as coming up to with the third sample, where my sample mean was $1.68. And again, same sample size being 36 prices. And of course, I don't want to waste any the viewers' time in terms of keep searching hopelessly for these, because they are now, at this point, as you are well aware, there are infinitely many of those sample means out there, provided they're all sample size under sample size 36, meaning 36 individual prizes on each sample. So now, this is a population, and forgive me that I keep mentioning the term being a population, because a population gives rise to the next idea right here. But so this is a population of sample means, and our sample mean here now is being regarded as the data. So we have learned a little while ago, that we can now use the random variable, to represent sample means. So we have been using random variable to represent our data, our population data. So now, any of these sample means, once we start seeing them as data, because in the end, a population of sample means, this is a data, a large data. And so I am now going to assign a variable's name. But instead of the traditional plain capital X, now I'm going to put a bar here to intentionally indicate that, yes, it's a random variable, but what it represents here is a sample mean value. So now I'm going to say, let's capital X with a bar here represent the mean. Now, I need everybody who views this video to look at my definition a little closely right here, but I define X, capital X bar, to be the mean of a sample. So any sample can have a mean value, any sample can have a mean, and so, but then generally any of those sample means is the value of the X bar. And so here X bar in this gas price, particularly in this gas price problem, capital X bar represent the mean of a sample of 36 prizes. So capital X bar is the mean of a sample of 36 prizes. And so now, I believe I am the only instructor doing this, but I feel it's convenient to do the following. When I was still teaching a face-to-face class with my face-to-face students, the gas prizes, the 36 prizes here, remind yourself that we must ensure all samples have equal sample size, in this case 36. So it's just me that I additionally put a subscript 36 here to indicate that, so it's in together here's one symbol for my random variable. So it's a capital X bar 36, represents the mean of a sample coming out from 36 prizes. And so outside of the gas prize study right here, then generally when I give a lecture to a face-to-face class with my students, then now I'm going to use generally a capital X bar to represent a sample mean. But then I'm going to go ahead but throughout my years teaching, I always put a subscript and right here indicating, so capital X bar with the subscript and represent a sample means from a sample of n values or n entries sometimes. So that's just the way how I use my notation for the rest of the video lesson here, and many other video lessons in the future that relates to the concept, to the study of sampling distribution of mean values. And now once again back to our study on gas prices here. Once I start introducing this random variable, this way of using random variable in a little bit unique in my own style right here, that I'm indicating the sample size being the subscript of the random variable capital X bar, then I start getting a lot of this kind of question. So what if we change? And this is a lot of time question that came from my students right here, but what if we change to a different sample size? say 100 prizes. I mean, what if on that day, June 1st, 2020, instead of picking only 36 prizes nationwide, I was instead picking 100 prizes nationwide, then what would I be using as a random variable? So in that case, if the sample size, and once again, keep in mind that once we decide to use a different sample size, then every other sample in our sampling distribution have to be the same sample size. So that means here I am going to use again in my style of using the random variable for this. So here, if each sample has 100 prizes as a sample size, then I'm going to use a capital X bar with a subscript 100, and that is going to be quite the similar meaning. It's any value here for capital X bar 100 is the mean of a sample. But in this case, a sample of 100 prizes nationwide. And so putting it all together, one random variable capital X bar with a subscript 36 represent a population of sample means, where each sample, a population of sample means, where n equals 36 in each sample. And now we realize capital X bar 100 that I briefly mentioned is now a population of sample means again. Sample means where sample size n is equal to 100 in each sample. And so here is another impact of naming different random variables to represent sampling distributions simply by indicating the sample sizes as subscript. These two random variables represent, even though there are population of X bar, but since we alter the sample size in each of our samples, these two are completely different. So here we're looking at two different populations. This one here and the other one there on the left. They are completely two different populations. And we will study more in depth how different these two populations are in our later discussions. So naming the random variables in this style is making it easier to differentiate the two different populations and to make students and viewers clearly realize the difference between the two populations that they may be working with there. And it is further important to realize the difference between a random variable that is named capital X bar and with a subscript n versus the usual plain capital X letter. These are all two random variable names, but this one means, so now after some thorough discussion previously, then any random variable is named this way right here, represents a population of sample means value where there are n, that's the sample size, so n values in each sample. So remind yourself, each value of this random variable is a sample means where it came out from a sample of size n, or there are n values in each sample. This other random variable we have been using throughout any time before this point of introducing this x bar sub n right here, then this is just simply a population. Just the plain capital X letter is a population of, here I have to use the term individual values. So as we're still talking about gas price and all that, and mostly I'm using gas price as the main big example in explaining the concept of a sampling distribution of a mean, then you see when anyone reads capital X no bar equals a 1.65, this is indicating this 1.65 here is one individual price, gas price. So it could be found in somewhere in Michigan, or it could be found somewhere in the state of Washington. It could be a gas price somewhere found in New York, but this is one single gas price. Whereas something like this, capital X bar, it's a sample mean automatically, but a subscript 36, for example, means and being equals to 1.77. So this one value is not a one single gas price, but it's a mean. It's mean of a sample of 36 prices. So that's the major difference between these two random variables. And there are two different populations as well.